Let's do this. Living with radiation. So, yeah, I don't know if you know, but stuff we call radiation's all around you. And I don't just mean harmful stuff, right? So, maybe I'll ask my newest students, Alexis or Cassandra. Ignore what you read. Before you came to class and before you came to the X-ray program, what did the word radiation mean to you? You don't have to give us a whole thing, but maybe just a one word. What one word response to if I say what's radiation?
Sunlight.
Sunlight. Good. Okay.
UV light.
What do you like? If you think about, is it good? Is it bad? If I say radiation, what do you immediately think? Think bad, right? So if you're left with it, good or bad, you think bad, right? Okay, good. So let's get a definition of what we mean by the word radiation and how that's different from like harmful radiation. Okay, good. So here we go. Radiation is defined as anything, any mechanism which transfers energy from one point in space to another. Okay. So then that begs the question. What question is being begged by saying that? What do you want to know once I say anything that transfers energy from one point in space to another? What extra little answer or question do you want to have answered when you hear that? You probably need probably the next point after hearing that is, what do you mean energy? Yeah? So, what is energy?
Power.
If let's say you have let's say power, good. Let's say you have no energy. What does that mean?
Get one of these.
Well, yeah. So no, let's say that though. Like you have no energy. You woke up in the morning and you literally say, "I got no energy." What do you mean when you're saying that?
You're drained.
Huh?
Drained.
Oh, sorry, you're drained. I thought I came from for some reason. So you're drained. Like what does that mean to you? Like you have things that you normally do in the morning, right? You get up, you brush your teeth, you get dressed, you come to work, right? If you got no energy, if you're drained, are those things easier to do, harder to do? Harder to do, right? Let's say the thing you want to go do is your work, right? Your job. Literally, you're doing some work. And you're low on energy, it's harder to do the work you want to do, right? So just using that, understanding of energy. Energy is the ability to do work. I don't mean in this case literally do your job. I mean change the position or velocity of anything, any particle, okay? Energy is the ability to move things, okay? Energy moves stuff. Stuff is matter. We're going to do a whole talk about stuff and energy later on, okay? That's our next talk, but I just want to kind of get you started with this idea that radiation is the transfer of energy from one point in space to another. Okay, if I do something quiet here, not so loud. If I drop this, right? I've made some radiation. What was the kind of radiation that I just made? Sound, right? I made mechanical waves. I let that thing hit the table. It shook the table a little bit, vibrated the air in the room, and made sound that got to each one of your ears, right? Who heard that the loudest? Lewis, because he's closest, right? Who heard it the quietest? Adrian, because he's furthest away, right? The energy moved through space, spreading out as it moved, right? Lewis was closest, so he got the most concentrated form of that energy. It was loudest for him. Adrian, you were furthest away. You got the least concentrated form of that energy, right? So you're further. The energy had more time to spread out. That is the inverse square law working, okay? Radiation transfers energy from one point to another in space. This can be in the form of particles, alpha, beta, and gamma particles, okay? More specifically, alpha and beta particles, which are the kind that come from radioactive atoms. Those are little tiny pieces of matter shooting through space, okay? Now, once let's say like take this pen cap right now, like huck it at the wall, yeah? After it hits the wall and stops moving, what does the pen cap still have? What kind of energy does it still have? Let's say it's now sitting here. It's got energy still, right? Not exact. I think it does have chemical energy, but I'm trying to get at the pen cap still has its mass. Okay, it still weighs something. Think of this as a little elementary particle. Okay, If I take a little elementary particle and through some radioactive decay event, it fires away from the atom and strikes some piece of matter, right? It's put energy into that thing that it hits, right? This particle put energy into that wall, okay? That's why it stopped moving. Yeah, it was moving fast as I threw it towards the wall. It hits the wall, and at the point when it hits the wall, it stopped its velocity, it stopped its momentum, right? Put energy into the wall. And what did you notice? Watch this again as the pen cap hits the wall. Does the pen cap just hit the wall and then drop straight to the floor? What's it do?
Comes back the way it came.
Bounces back at me, right? The energy is returned back into the pen cap, right? The pen cap hits the wall, deforms a little bit, and then the energy is put right back in, and it doesn't keep going that direction. It comes straight back at me, right? This is part of the conservation of energy, which we'll talk about next time too. But energy can be in the form of particles. Think about particles as little pieces of stuff. This is a piece of stuff, right? So that's a representation of a particle, but particles are actually very small. They're pieces of atoms. Alpha and beta particles are the primary ones that we talk about. We'll deal with those later, but they are helium nuclei and electrons. Particulate radiation, that's all radioactivity. Mechanical waves are forms of radiation, right? I made that cassette hit the table and it made sound, right? That's mechanical radiation. What needs to be between me and you for that mechanical radiation to reach your ears? Air, right? So if I suck all the air out of this room, let's say we have put on space helmets and I suck all the air out of this room, right? And then I do that again. What happens? No air in the room means no sound, right? So in order for the energy, for mechanical waves, in order for the energy to get from me to you, or from the point where I did the thing, right? From there to you, there has to be a medium. There has to be something between me and you, okay? Such as air in the room or water, right? Water has mechanical waves too, like waves in the ocean, right? If there's no water, there's no waves in the ocean, yeah? Okay, mechanical waves need a medium to travel through, okay? They need something between me and you. Then you get to this next type, electromagnetic waves. Electromagnetic waves are transfers of energy from one point in space to another that, importantly, do not require a medium. Think about, you go outside at night and you see the stars, okay? What's between the Earth and the stars? Space, right? Which is just empty, right? For all our intents and purposes, space is empty between the stars and us. So, you guys know how far away the nearest star to us is? The closest one. No, ignoring our sun. That would be the smart aleck answer. You could have done that, but you missed it. So the closest star to us is 4 light years away. Okay, but you can see it. The star's name is Alpha Centauri. You can find a little map and you can see it in the night sky. Okay, 4 light years away. Light travels 300 million meters per second. Every second it travels 300 million meters. Do that for 4 years. That's 4 light years of distance. It's a long ways, right? Okay. But the light still gets to us, yeah? So you look out in the night sky, you see a little pinpoint of light in the sky, okay, from Alpha Centauri. There is nothing between us and that light source. There is no medium between us and that light source. It's just empty space, okay? No air, no nothing, no medium between us, okay? But the light still reaches us nevertheless. Electromagnetic waves are referred to as self-propagating waves. In order for sound to travel, you need a medium to propagate through, to move through. Light waves do not need a medium. They are their own medium, period, okay? That's really weird, okay? Most waves need something between me and you. Most forms of radiation need something between me and you. Electromagnetic waves are self-propagating. They are their own medium. Okay, they are a wave in the electric and magnetic field, and if that means nothing to you, it will eventually, okay? Electromagnetic waves are light, like visible light, X-rays, radio waves, infrared, ultraviolet, microwaves. Visible light, what are the colors that you can see in the visible spectrum? Colors of the rainbow. Red, orange, yellow, green, blue, indigo, violet. 7 colors, right? 7 colors of the rainbow. In fact, there's only 6, but Newton, who did this, liked the number 7, so he took indigo and violet, which is just purple, and he split them up into 2. So red, orange, yellow, green, blue, purple.
He was a little crazy.
He
Like a religious.
he's a little wonky, yeah.
He tried to like decode the Bible and then end up going crazy.
Yeah. You heard a little bit about him, yeah. So he's a little funky, kind of a funky guy, but super smart. I mean, all the smart people are going to have some quirks, right? Mental illness is going to follow intelligence or artistic creativity, and he's no different. Yeah. So what I want to point out though is that this thing we call the electromagnetic spectrum, which is all the ranges of different types of light, right? If the electromagnetic spectrum is like yay big, right, as wide as my arms can be, the visible light spectrum, the stuff that we can see, is this tiny little sliver right in the middle, okay? There is so much more in the electromagnetic spectrum, electromagnetic waves, that we cannot see than we can see. We are only perceiving a small fraction of what is actually happening. By the way, there's good reason for that, right? Where did human life evolve? Here on Earth, right? And here on Earth, what's our primary source of light? The sun, right? And you would not be surprised to learn that the sun's primary output of light is in the visible spectrum. So we evolved to see visible light because that's what the sun puts out. Okay, so it's not some conspiracy that we can't see everything for some other reason. We see what we see because that's what the sun puts out. Okay, good. So yeah, but light's in there. X-rays are in there. Infrared, ultraviolet, radio, TV, all that stuff. Wi-Fi stuff is all radio waves and stuff. Ultraviolet is kind of interesting. Ultraviolet is the type of light that's more energetic than indigo and violet, right? And ultraviolet is not visible to us, but harmful to us. Okay, it hurts our skin, right? It gives us skin cancer and stuff. Some animals can see ultraviolet light. Certain birds, crows, I believe, crows, ravens, those kind of birds can see in the ultraviolet spectrum. Some insects too, like I know, like was it bees, hummingbirds, I think can also see in ultraviolet. But so some animals see in wider spectra than we can. Okay, for good reasons. They need to be able to see certain flowers and stuff like that. Some other animals, like certain reptiles, like certain snakes, can see in the infrared spectrum. We see red, but we don't see anything below red, infrared. Which is, by the way, what we put out as infrared is heat, okay? So some snakes can see heat, yeah? They see the infrared spectrum, kind of like a thermal camera would see. Snakes can do that. So this spectrum of light, we get a small sliver of it. Other animals get different slivers of it. And but that's what it is. Electromagnetic waves are things like light. So the only difference, let me rephrase this. Light and X-rays, visible light, X-rays, radio waves, all this stuff, they're all the same kind of thing. It's an electromagnetic wave, okay? They are only different in the size of the wave, how far apart the waves are. That's all that differentiates them. Wavelength, which is how far apart the waves are from each other, is related to energy of the wave. Energy of the wave for us is related to the color we can see. You probably know that like blue light at nighttime is bad for your eyes, right? So you get off your devices, yeah, which you all do, right at like 8 o'clock at night, right after dinner, you all get off your devices. What do you actually do? You stay on your devices, right? And what does that do? Continues to stimulate your brain. Well, guess what? Your brain doesn't know that you're looking at a phone. Your brain just gets wavelengths of light and it goes, oh, well, there's still blue light coming in. It must be still daytime, okay? And it stops production of things like melatonin in your body, doesn't really activate your circadian rhythm to go to sleep, and guess what? You stay up late at night, right? Poor sleep cycles, affects health, and all this kind of stuff, right? That's why they advise you to get off your phones and stuff. Well, your phone people got smart, and they started putting in light filters in your phones that you can set them to turn on at certain times. You can put on your phone on nighttime mode, right? Changes the background color, it changes sort of the hue of the screen. Notice the screen looks a little bit more yellowy when you do that, right? You can get UV and blue light filtering glasses if you work at computers all the time, right? So to help you with this. But that's the deal. It's the same kind of thing. All these electromagnetic waves are the same kind of thing, just different in their energies. Good. All right, so let's move on. By the way, if it wasn't clear, this is the primary type of radiation that you need to get very familiar with. You need to know the other types to contrast against this, but we need to know about electromagnetic waves because that's what X-rays are, okay? That'll be in the last talk. We'll really get deep into that. But let me read a few things. So while particulate and mechanical waves are both classified as forms of kinetic energy, and let's pause there for a second. What's kinetic energy? Movement, right? So does this pen cap have kinetic energy right now? What do I need to do to give that thing kinetic energy?
Needs energy.
I need to put energy into it, right? So I need to like pick it up and then I can drop it too. I can pick it up and move it up higher and I can drop it. I gave it energy by just putting it into a position, yeah? I can also like throw it and put energy in that way, right? But I've got to, if I just leave this alone, what is it going to do? Yeah, it's one of Newton's laws, right? An object at rest will remain at rest until acted on by an outside force. That's at rest right now, has no kinetic energy, and if an outside force acts on it, such as myself, or anything else, my cat comes by and swipes it off the countertop, something like that, right? That's an outside force, okay? Once it is put into motion, it has kinetic energy, okay? It's like when I threw this pen cap at the wall, boink, right? I took and gave it kinetic energy, and then when it hit the wall, it put all that kinetic energy into the wall. Newton says that every action has an equal and opposite reaction, which is why the wall hits back, okay? So you hit the... Enrique can tell you this. I've heard he's a fighter, so he can tell you this, that when he hits something, those things hit back, right? He throws a punch, and the thing he hits is going to put force right back into his hand and hurt him too, right? So that's the deal, right? Electromagnetic waves, mechanical and particulate radiation are kinetic energy. It's things having motion, okay? The important part of this is a thing is made of mass. Right? Stuff, matter, right? For this to have energy beyond its mass energy, it has to be in motion, okay? And it can sit still. Things with mass can be still, okay? Once they have kinetic energy, they're moving. However, electromagnetic waves are not kinetic energy. Even though it's energy moving through space, we cannot classify it as kinetic energy because electromagnetic waves are not made of stuff. And this is sort of a weird thing to get across. Electromagnetic waves, X-rays, light, it's not mass. They're not a thing moving through space, okay? It's a wave in a field. That's all it is, okay? It is a form of potential energy. Potential energy is the energy of position, the ability to carry energy and do work once you get to where you want to go, right? Electromagnetic waves transfer energy without moving any physical object. Electromagnetic waves, and we'll learn this in the last lecture, they are not massive, okay? And if you don't have mass, you ain't matter, okay? That's the deal. You don't have mass, you don't matter. Electromagnetic waves consist of a fluctuation of electric and magnetic fields. They are a double wave in the electric and magnetic field. Don't worry if that bothers you right now. It will forever, I promise you. It's not going to get better after you learn all this stuff. You're just going to know more and go, a wave in electric and magnetic field, and it's going to bug you for forever. But that's what it is, okay? They are massless waves in the electric and magnetic field. They don't carry anything except for their intrinsic energy. They don't have any mass. Okay. Again, that should mean a lot, but it might not hit hard until you get more of this under your belt. Because this is a big idea here, that they have no mass but still carry energy. Okay. So, all right, so that's radiation. What we mean by radiation is energy moving through space. We've got particle radiation, we've got mechanical waves, and we've got electromagnetic waves. Okay, those three types. Hang on. Quick so I don't run out of computer power. So, at the beginning of this, it was Cassandra that told us when I said, what do you think of when you think of radiation, good or bad? And you answered bad, right? That's a really good way to think about it, because when you hear radiation, typically we're not talking about the good stuff, right? We're not talking about sound waves usually, right, or water waves. Typically we're talking about, when we say radiation, we're talking about stuff that's harmful, right? So let's make a new term for what we mean by harmful radiation. We call harmful stuff ionizing radiation. So visible light, not harmful. Okay, expose me to all the visible light you want, you're not going to hurt me, okay? Now, you can go out in the sun and get sunburnt, right? It's not the visible light that's burning you. It's the stuff you can't see. The UV stuff, right? The ultraviolet. So you got in the sun, you're getting a bunch of visible light, but you're also getting a bunch of stuff that you can't see, ultraviolet, okay? That's what's hurting you. That stuff is ionizing, okay? Ionizing for one does not mean harmful, okay? But ionizing radiation is harmful. The word ionizing means something different. Some forms of radiation, including particles and X-rays, are capable of ionizing the atoms of the matter that they hit, okay? So you have atoms, like this one here, and a happy atom just minding its own business, okay? So this is in something, doesn't matter what it is. This is in some piece of matter, maybe part of you, and it's just kind of minding its own business, being a happy atom. Happy atoms have electrons orbiting around them. That's what's being shown as these little green balls here. They're not little green balls, but works for the picture. But it's got electrons orbiting around a dense nucleus. Electrons orbit the nucleus. Protons and neutrons, the other particles that atoms are made of, sit here. Atoms get their heft, their mass, from the nucleus. Okay? And the nucleus has a positive electric charge, and it holds on to electrons which have a negative electric charge. You guys probably know that opposite charges attract and like charges repel. Kind of like when you take two north poles of a magnet and they push apart, right? You have to north and south poles touching. Anyways, positively charged nucleus, negatively charged orbiting electrons. Happy atom just minding its own business. It's got the same number of protons and electrons. That's when atoms are happy, neutral. Okay, minding its own business. So along comes a photon. And if this photon has enough energy, this photon is a piece of light, particle of light, right? If it's a visible light photon, it just passes right on through the atom, doesn't touch it at all, okay? But if it's an X-ray photon or an ultraviolet photon, okay, and it hits in the right spot, it can hit an electron and just dump all of its energy into the electron. And that electron will fly away from the atom, okay? The electron is removed from the atom, and now the atom is down one negative charge. So the atom now has more positive charges than it has negative charges. What will be the net charge of the atom, positive or negative? Positive, because we've lost one of our negative charges. If we've got 10 negative charges, 10 positive charges, and you take away one of my negative charges, right? Now I have a charge of +1. Yeah, the atom has been positively charged. Not only that, the atom has a charge now, but this guy over here, who is not minding his own business anymore, but now shot off into the space around the atom, that has a charge too. And its charge should be is -1, right? Negative charge. So now you've got a positively charged atom, a negatively charged electron. And guess what? These negatively charged electrons and positively charged atoms, they're called an ion pair, and these are now going to go around and cause harm, okay? Maybe this atom was part of your DNA, okay? Now it's going to break apart the DNA strand in a spot, okay? This electron is going to go flying around and crash into another part of your DNA, breaking that part, okay? Ionization, for one, ionization is the creation of charged particles. Charged particles are what we just talked about here. Creating charged particles, ionization, will lead to chemical changes which can result in harmful biological changes. So if I shoot some x-rays at this tabletop, it's not going to fall apart. Not going to be harmed, okay? This tabletop doesn't get harmed because this tabletop is not biological. It's not alive, right? Presumably if this is made of real wood, at one point it was alive, yeah? But not right now, right? It's inanimate, it's not living, it's not changing on a regular basis. If I ionize some of the atoms in here, no big deal, okay? But I ionize some of the atoms in a person who has to go on living, right? If it's the right kind of atoms in the right way, I can make changes to the body that are bad, right? Mutations in the DNA sequence, harming individual cells of the body, right? There's a number of things that can happen, but anyways, harmful biological changes can happen from ionizing radiation. This is the principle behind why UV radiation is bad, because it can cause ionization, and why we try to avoid it. Yeah?
So you know how when we put the cassette on the buggy, and then, so they're laying on the bed, right? But like there's like a little like mattress.
Yeah.
It's like yellowish now. Is that because it's like?
It's probably more just from like oil exposure and like light in the room exposure and breaking. Just the color pigments get broken down over time. Now, in principle, some of those color pigments over time can be broken down by the X-rays. But it's really just the wearing of the material. It's normal wear and tear. But you guys know, like things like you got a plastic play structure for your kids or something like that, or anything that's plastic tends to fade. Plastic like yard chairs, right? They fade over time, right? The pigment in them gets broken down by ultraviolet. So there's some chemical changes that happen to inanimate things, but we don't really care because they can't die, right? They can just fade a little bit. Yeah. So we worry about with people, though. People, animals, things like that. Unfortunately, there's no good regulations for animals for radiation use, but for people there is. We try to, we do things like the ALARA principle. Keep our exposures as low as reasonably achievable, right? Okay, so now that you know what radiation is, you know what we mean by harmful or ionizing radiation, let's talk about where it comes from. About 1/2 of all the radiation you get in a year does not come from X-rays. About half of it comes from X-rays, medical radiation. But the Earth is radioactive. That's where we get all of our radioactive chemicals from, radioactive elements from, right? We got to get it from somewhere. It comes from the Earth. The stars and other star explosions called novae, when stars blow up, they spread their particles around the galaxy, right? And that's what, by the way, that's what we're made of, right? Carbon, all these heavy elements, right? Come from stars exploding and spreading their elements around the universe, really. And so we are, we from the Earth, but our star is just like a second generation star. It got all of its stuff to work from other stars exploding. So we get radioactive particles coming from stars and other planets, stars and other stars explosions, but usually most of that is absorbed and stopped by our atmosphere. Their atmosphere and our magnetic field, right? If you ever heard of the aurora borealis, the northern lights, right? That's what it is. It's radioactive and high energy particles, cosmic rays, striking our atmosphere and being funneled into where the magnetic field lines come together at the North Pole, northern magnetic pole, and creating these cool light shows. Okay, there's also one at the southern pole too, called the aurora australis. It's the same type of thing, but happening at the southern pole. But that's the deal, right? We get sources of radiation from all over the place. The universe sends us radiation. Our own star sends us radiation. A lot of it's stopped by our atmosphere and magnetic fields, but some of it does get through. Minerals in our own buildings can be rich in uranium, especially if they're things like concrete. Your own bodies. You have radioactive atoms in your own bodies. You have potassium in your body. You need potassium to be alive. You will die if you run out of potassium. Okay, sodium and potassium are what generates the energy for your nervous system to function. Okay, so you low on potassium or you're low or high on sodium, you get like muscle cramps and stuff. You need potassium in your body. Well, potassium has a radioactive form called potassium-40. You get that from any food that you eat that has potassium in it, and so you get radioactive chemicals in your body. You have them. They're just there. For every minute of your life, you have about 5,000 radioactive decay... per second. 5,000 per second. 5,000 radioactive decay events per second in your body, okay? So it's happening all the time around you. You cannot possibly get away from it. Even if you went, down to the deepest cave on Earth and sort of put yourself in a lead box, right? You're still going to be emitting radiation from within your own body. We can measure this. And so you see this, you can do this with foods like bananas, which are rich in potassium. You can put a Geiger counter up to the banana and watch it go click, click, click as it clicks off radioactive decays. And then you eat the banana, and those they get inside your body. Odd sources of radiation. Smoke detectors, the little element in the smoke detector that detects smoke relies on radioactive decay, so radioactive elements. Glossy magazines. The glossy magazines, I don't have any glossy magazines in here, but that's a good example. The cover of your textbook, that's a little glossy, right? They make that glossy covering from a clay. The clay is rich in uranium. So there's uranium in there, okay? Not a lot, you can't see it. We used to make, the early, first parts of the 20th century, we would make cups and plates and bowls and all kinds of stuff out of uranium enriched glass because it was cool looking, a nice, really cool green color. I'll bring some in sometime. We've got some to bring in, but you can literally turn the lights off in the room and see it glow. It's that radioactive.
Like 10 pounds.
Yeah, here you go. Glossy magazines, camping lantern mantles, cigarettes are radioactive, lead and polonium. There's radioactive versions of lead and another element called polonium. That's in cigarettes. And a bunch of it goes into the smoke that you don't inhale, but you inhale a significant portion of it if you smoke cigarettes. So you're getting radioactive elements going into your lungs. The bad part about that is that cigarettes only emit particulate radiation, and it stays inside of your lungs like indefinitely, which is why lung cancer is a big problem with cigarettes. Bananas, we mentioned bananas already, potassium 40. Drinking water. I encourage you to go home, go to your city's mutual water company website, and look up your water report for where you live. You will have radioactive elements in the water. It's just part of the deal, okay? We live here on Earth, and there's radioactive stuff on Earth, and it's in our water, okay? Some places have more than others, but there you are. Radon gas. Radon is a breakdown product of uranium. When elements break down through radioactive decay, we call it transmutation. Uranium turns into other less radioactive things as it ages, and radon is one of these things that uranium turns into. Radon is a gas, and that gas can accumulate in basements of poorly ventilated homes. Okay, this is usually a bigger problem near mountainous areas, and other areas actually like the Midwest is a good example where this is a problem. But yeah, you have to have it's in the building code of your building. Like your buildings are built in a specific way, right? If you're a contractor that builds buildings, you can't just build any old building. You have to follow specific codes, right? So you build the building correctly. And one of those things is making sure if you have like a basement, there's proper ventilation so radon gas does not build up in your basement. You may have never heard of radon, but it accounts for 2/3 of all of the radiation that you get from natural sources. So limiting our exposure to it is important. Let's talk about some radiation disasters. There's only been a couple, okay? And so we actually don't have that much data from there's not dozens or hundreds of radiation disasters that have happened. There's only a handful, okay? Some of them were very small scale, and we don't actually talk about them, but some of them are actually large scale, like the ones that we mentioned here. Hiroshima and Nagasaki bombs, Fat Man and Little Boy, those bombs dropped at the end of World War II to end World War II that were dropped on Japan from the United States. Those were a real deal disaster. I mean, literally 100,000 people on the first bomb were completely vaporized instantly. Okay, everyone who survived the blast got lethal doses of radiation. Lots of them died, some survived, and some went on to have children. Some were children when this happened. And there's ongoing occurrences of cancers, leukemia, things like that in the populations of these people. So it's a big problem, and still to this day they're still dealing with the effects of this. It'll take hundreds of generations for this to work itself out of the gene pool. Other real disaster, the only other real big one is Chernobyl. Chernobyl in the Ukraine in 1986 emitted an amount of 50 million curies of radioactivity. Don't worry about what a curie is, just remember the 50 million part of this, okay? Because the next one is an imagined disaster. Now, we're all maybe not old enough to know this. I think no one here was born before this, but 1975, a power plant in the United States had a mini meltdown event and emitted 17 curies of radioactivity. This, not the Chernobyl thing, but this is why everybody's scared of nuclear power plants in the United States. We don't like nuclear power plants because one of them one time had a little tiny meltdown. Ukraine, actually, theirs exploded. Chernobyl literally exploded. The whole building, the whole reactor, it completely exploded because it overloaded. And went critical, but yeah, complete blown up. This is not bad. 17 curies compared to 50 million curies. This 50 million curies of radioactivity contaminated an entire section of Ukraine that cannot be populated anymore for like ever. Like ever again. It contaminated the world's drinking water, the world's air. It really made big problems for the entire world. Okay, and for forever. I mean, this is thousands of years we're talking about of it'll stick around for. And the imagined one is 3 Mile Island in the United States. We'll talk more about these three things when we get back around to radiation safety towards the end of your guys' program. And most of you will be out by that time, like all of you. Yeah, I'll have a bunch of new students. You guys will be the senior ones by that time. But there you are. So that all sounds pretty scary, right? Let me just finish up with some reminders to make it sound less scary. The benefits of taking x-rays and learning. Remember, we started off with why this is so cool. We learned something new about the body with x-rays, right? The benefits far outweigh the risks of radiation in medicine, okay? Sometimes the benefits don't outweigh the risks, like if they're pregnant or not hurt, right? That's why we can't take x-rays on you, right? You're not hurt. There's no benefit to taking x-rays on you, right? Aside from like student practice, but there's no medical benefit for taking x-rays on you, so we don't. But in medicine, there's a benefit. We learn something about the body when something's wrong with the body, right? Benefits outweigh the risks. Nonetheless, because the effects of radiation are cumulative, they build up over time. Radiation is managed with a healthy respect, and exposure to all patients are kept ALARA. So if you haven't heard that word before, ALARA, as low as reasonably achievable. It's a philosophy that says, keep your doses low, but still get what you need to do done. Do what you need to do with the least amount of radiation. Why do we know all of this stuff, and why are we able to, be safe around radiation? Because people died. Okay, accidents and diseases in early radiation workers brought to light the need for judicious use of lead aprons, shielding devices. The incidence of various disease among radiographers now is no different than for the overall population. We don't die earlier than any other occupations. We don't get diseases more than any other occupations. We have a safe job nowadays because lots of people got hurt and died, early on figuring this stuff out. So modern radiography is classified as a safe profession with associated risks about the same as any other low-risk job, secretaries, clerks, school teachers. There's lots of other riskier jobs than this one. This one's a very safe job, but we still get to use radiation, which is cool, right? So there you are. That is the end of everything I want to say today.